Hello everyone, welcome to Cyber Hashira. Today's video is about performing encryption using PKCS11 API. I will teach you how to perform encryption using a symmetric key and an asymmetric key. Let's get started. These are the functions that I will be discussing in this video. There are a total of 8 functions. 4 of them are used for encrypting data and the other 4 for decrypting data. I'll start with Encrypt init. In PKCS11, this function is used to initialize an encryption request. Before a token begins encrypting data, it needs some information such as the encryption algorithm and the key to use. Encrypt init initializes the memory with all that information. This function requires 3 arguments. The first argument specifies the session handle to use. It is of type CK session handle. The second argument is of type CK mechanism. This argument is used for specifying the encryption mechanism to use. For example, if an application is requesting to use AES encryption, then it may specify CKM AES CBC pad as the mechanism to use. And the third argument is of type CK object handle. This argument carries the handle number of the key required for encryption. So if an application wants to perform AES encryption, then it would pass the handle number of an AES key. These are some of the return codes that Encrypt init may return. Feel free to pause this video if you would like to read it. You can learn more about this function on page 139 of PKCS11 Manual. Next function is Encrypt. This function is used for single part encryption. There are 2 ways to perform encryption, single part and multi-part. I will explain what they are later in this video. The first argument of Encrypt is a session handle number. Second argument is of type CK byte PTR. This is the reference to the variable that holds the clear text. Third argument is of type CK ulong, representing the size of plain text in bytes. For example, if the plain text consists of 32 characters, then the size would be 32 bytes. Fourth argument is a reference to the variable where the encrypted data is stored. This is the memory address where Encrypt would send the encrypted data. Fifth argument is the length of encrypted data. This is useful when you want to determine the size of encrypted data before allocating memory to it. I will explain this when I'm discussing the sample codes I prepared for this video. And these are some of the return codes that Encrypt may return. Pause this video if you would like to read it. You can learn more about this function on page 140. Before I move on to the next function, let's take a moment to discuss single part and multi-part operation. Cryptographic operations such as encryption, signing, and hashing can be performed as a single part and multi-part operation. Single part operations involve processing the entire plaintext in a single attempt. They are most suitable for small-sized data. For example, if you have a short text or a message, a single part operation would allow you to easily encrypt all of that data in a single attempt. Most hardware tokens process plain data directly in the hardware. Typically, these devices have a very small amount of memory, which may not be sufficient for handling large amount of data. So, multi-part operation is more suitable for such devices. In a multi-part operation, the plain data is divided into small size chunks, and then each of those chunks are processed separately. Now that you know what a single part and a multi-part operation is, I will now talk about Encrypt update. This function is used for multi-part encryption. To utilize it, an application needs to first divide large plain text into smaller chunks, and then use Encrypt update to encrypt those chunks. The number of times this function is executed depends on the number of chunks. For instance, if a large plain text was divided into 10 pieces, then Encrypt update may need to be executed 10 times. C encrypt update requires 5 arguments. The first argument is a session handle. The second argument is of type CK byte PTR. This is where a small part of a large plain text is passed. Third argument is of type CK ulong, indicating the size of that small chunk of plain data. Fourth argument is the reference to the variable where the encrypted data will be stored. And the last argument is going to be the length of that encrypted data. Here are some return codes that C encrypt update is expected to return. Feel free to pause this video if you want to read them. You can find this information on page 141. C encrypt final is used for finalizing the encryption after all pieces of plain text has been processed. This function produces the last remaining portion of the ciphertext. C encrypt final takes 3 arguments. The first argument is a session handle. The second argument is the location that will receive the last remaining portion of the encrypted data. And the third argument is of type CK ulong, representing the length of the encrypted data. And these are some of the return codes that C encrypt final is expected to return. This information is available on page 141 and 142. Now let's talk about the functions used for decrypting ciphertext. We'll begin with C decrypt init. This function is used for initializing a decrypt operation, and it needs 3 arguments. First argument is a session handle. The second argument is the mechanism, or you can think of it as the algorithm needed for decryption. And the third argument is the object handle of the key needed for decryption. And these are some of the return codes that C decrypt init may return. This is not a complete list. You can read more about C decrypt init on page 144. After initializing decrypt operation, the next step is to start decrypting data. C decrypt function is used for decrypting and encrypted data as a single part. This function requires 5 arguments. Similar to other PKCS11 functions I've discussed so far in this video, the first argument of C decrypt is a session handle. Second argument points to the location of the encrypted data that you want to decrypt. Third argument is of type CK ulong. This argument is the length of encrypted data that you want to decrypt. Fourth argument is the location where you want to write the decrypted data. This is a byte array. And the fifth argument is the length of that decrypted data. These are some of the return codes that C decrypt may return. You can read more about this function on page 145. C decrypt update is used for multi-part decryption. Large encrypted data can be broken into smaller pieces and decrypted one by one. This function requires 5 arguments. First argument is the session handle. Second argument is the memory address of the variable containing a part of an encrypted data. Third argument is the size of that small piece of encrypted data. Fourth argument is the location where you want to write the decrypted data. And the fifth argument is the length of the decrypted data. These are some of the return codes that C decrypt update may return. More information on C decrypt update is available on page 146. And the last function for today's video is C decrypt final. This function is used for finishing a multi-part decryption process. This function requires 3 arguments. First argument is the session handle number. Second argument is the location where the remaining decrypted data or the plain text will be written. And the third argument is the length of that decrypted data. And these are some return codes that C decrypt final may return. More information about C decrypt final is available on page 146 and 147. Okay, so these are the 4 samples that I will be discussing in this video. I will start with CKM DES3 ECB. Okay, so this sample will generate a DES3 key, and using that DES3 key, it will try to encrypt plain text using ECB mode of encryption. Let me show you how it works. Before I begin, let me first explain the variables that I've declared here. So there's a variable called obj handle. This is of type CK object handle. This variable will be used for storing the handle number of the DES3 key once it has been generated. Plain data, this is the this is the plain text that I will be using to encrypt. It's just numbers. Then there's a variable called encrypted data. This is of type CK byte. It's a pointer. This variable will be used for storing the encrypted data. And then I have another variable called decrypted data. This will be used for storing the decrypted data. Then I have two more variables of type CK ulong. ENClen will store the length of encrypted data, and DEClen will store the length of decrypted data. Okay. And this is all the usual stuff that I do in my sample. Okay, here it is. So generate DES3 key. This is a function that will generate a DES3 key. These are the attributes that I will be using. I'm sure if you have watched all my previous videos, then you are already familiar with all of this. Let me show you the function where encryption and decryption is happening. So this is encrypt data and this is decrypt data. Let's start with encrypt data. This function will be used for encrypting the plain text. Inside this function, I have declared a variable called mech. This variable is of type CK mechanism, and the value is CKM DES3 ECB, which means this function will encrypt the plain text using a DES3 key and ECB mode of encryption. Okay. And the first PKCS11 call that I'm making inside this function is encrypt init. This function takes 3 arguments. The first argument is a session handle number. Second argument is the mechanism. I have already declared the mechanism here. Third argument is the object handle number of the DES3 key. I have already generated the DES3 key here. We have the handle number. I'm simply passing that handle number to this function. The next function is encrypt. This function takes 5 arguments. The first argument is the session handle number. Second argument is the plain data. This is a plain text that I want to encrypt. Third argument is the size of that plain text. I'm putting -1 here so I could remove the null character from the plain text. I am passing null as the fourth argument because I have not yet reserved any memory to store the encrypted data. So this is a variable that I will be using to store the encrypted data, and it currently does not have any memory reserved for it. The fifth argument is ENClen. This is going to be the length of the encrypted data, and I will use this value to reserve some memory, and that's exactly what's happening here. So the value that I'm getting from this function will be passed here, and I am assigning some memory for encrypted data. And once we have appropriate amount of memory set to encrypted data, I will repeat that same encrypt call. So encrypt, the first argument session handle number, second argument is plain data. This variable contains the plain text. Third argument is the length of that plain text. Fourth argument is the variable that will receive the encrypted data. We have already assigned memory to it. And the fifth argument is a variable that will receive the length of that encrypted data. And once this data has been encrypted, I have a separate function that would display the binary data as hex. Okay, let's now have a look at decrypt data. This function will decrypt the encrypted data. And the code inside decrypt data function is almost identical to the code written inside encrypt data. So there's a variable called mech, which is of type CK mechanism, and the value is CKM DES3 ECB. This is a mechanism that will be used to decrypt the encrypted data. The first PKCS11 call inside this function is cdecrypt init. This is used for for initializing the decrypt operation. This variable takes 3 arguments. The first argument is a session handle number. Second argument is the mechanism. I have declared the mechanism as CKM-3 ECB. Third argument is the handle number of the DES3 key that we will be using for decryption. The next function is cdecrypt. This function takes 5 arguments. The first argument is the session handle number. Second argument is the encrypted data. Third argument is the length of that encrypted data. Fourth argument is null because we haven't set any memory buffer to decrypted data. And the fifth argument is the length of the decrypted data. Once we have retrieved the length, I will use that length to assign some memory to decrypted data variable. And then we will repeat that same decrypt function again. So again, the session handle, encrypted data, length of encrypted data, decrypted data variable with the memory assigned to it, and the length of that decrypted data. And once the data has been decrypted, printx function will display the binary data as hex. Okay. And then finally, we have the main function, which is going to first load the PKCS11 library, connect to the slot, generate the DES3 key, and it will first print the plain data as hex. Then it will encrypt the data, decrypt data, and then disconnect from the slot. All right, let's compile this code. To compile this code, I will run the command g++ ckm des3, okay, and I will output this into this file name. I want to include headers from the include directory, and this sample is for Unix Linux environment. Okay. I need the slot number. Here's the slot number. So CKM, the slot number, and this is my user password. And here it is. So this is the plain data. This is the encrypted data as hex, and this is the decrypted data. It matches with the plain data. Okay, let's have a look at our next sample. Our next sample is CKM ASCBC pad. So this sample will generate an AS key, and it will use that AS key for encryption. Let's have a look at the variables that I've declared. So there's a variable called obj handle. This variable is of type ck object handle. This variable will store the handle number of AS key. Then I have another variable called iv, which is of type ck byte, and this is a byte array. I will be using this value as the initialization vector. CBC mode of encryption requires an initialization vector, and this value will be used as that initialization vector. For plain data, this is the plain text that the sample will try to encrypt and decrypt. Encrypted data will store the encrypted data. Decrypted data will store the decrypted data. They both have the value of null. Both are of type ck byte, and they are pointer. No memory assigned to them. Then ENCLEN will store the length of encrypted data. DECLEN will store the length of decrypted data. Both of them are of type ck ulong. Okay, let's scroll down. This is just the usual stuff: load library, free resource, print hex. Oh, by the way, this is the function that this sample uses for printing binary data as hex. If you want to have a look at it, check operation, connect to slot, disconnect from slot, generate AS key. This is a function that will generate the AS key. The size of that AS key is going to be 32, and these are the attributes that will be set to that key. It's going to be a session object, and once the key is generated, it will store the handle number in this variable obj handle. Let's scroll down. Okay, here's encrypted data and here's decrypted data. Let's start with encrypt data. Okay, I'll focus on the differences. So encrypt data, this function will encrypt the plain text. Inside this function, I have declared a variable called mech. This is of type CK mechanism. And the value that I've specified, first we have specified the mechanism that I want to use. This is CKM ASCBC pad. The second argument that I'm passing is the IV and then the length of that IV. I'm putting -1 to remove the null character. The first PKCS11 call inside this function is cencrypt init. I'm passing the session handle number, the mechanism that I declared here, and the object handle number of our AS key. The second PKCS11 call is cencrypt. This function takes 5 arguments: the session handle number, plain data, size of that plain data. I'm passing null because we don't have a memory buffer assigned to it, and the length of the encrypted data. This variable will receive the length of that encrypted data, and we will use this length to assign memory to encrypted data variable, and then we will repeat the cencrypt call again. So the first argument, session handle, plain data, size of plain data, encrypted data with the memory assigned to it, and the length of encrypted data. Once this data is encrypted, I will print the encrypted data as hex. Okay, let's see what's happening inside decrypt data. Almost identical code inside decrypt data. So there's a variable called mech of type CK mechanism. This has CKM ASCBC pad, the IV, and the size of that IV. The first PKCS11 call is decrypt init, which has the session handle number, the mechanism, and the object handle number of the AS key. The second PKCS11 call is decrypt, that has 5 arguments: session handle number, encrypted data, the length of encrypted data. We are passing null because currently decrypted data does not have appropriate memory assigned to it, and the length of the decrypted data. Once we have received the length of decrypted data, we will use that information to assign memory to decrypted data, and then we will repeat decrypt call. So session handle number, encrypted data, length of encrypted data, decrypted data, and the length of decrypted data. And once this data is decrypted, print hex function will display the binary data as hex. Okay, let's scroll down. This is our main function, and inside main function, load library, connect to slot, generate AS key. This will generate the AS key which the sample will use for encryption. It will first print the plain text as hex. It will encrypt the data, decrypt the data, and finally disconnect. Okay, let's execute this sample. We'll first get the slot number. Okay, here's the slot number. Clear the screen. Okay, so G++ CKM AS output CKM AS, include all headers inside include directory, and D mix. Okay, CKM AS, here's the slot number, and this is the user password. Okay, here's the output. So PKCS11 library loaded, AS key generated. This is a plain text. This is the encrypted data. And this is the decrypted data. As you can see, it matches with the plain text. All right. The next sample that I'm going to discuss uses RSA algorithm. Okay, so this sample will generate RSA key pair, and then it's going to use that key pair for encryption. Let's talk about the variable. Most of it is similar. So I have declared two variables of type CK object handle. H public is going to store the public handle number, and H private will store the handle number of the private key. I said public handle number, I meant public key handle. Okay, this is a plain data that it is going to encrypt. I have a variable called encrypted. This is going to store the encrypted data. Then there's another one called decrypted. This is going to store the decrypted data. And then we have two more variables of type CKUlong. ENClen is going to be the length of encrypted data, and DEClen is going to be the length of decrypted data. Let me show you the part where the key pair gets generated. Okay, just the usual stuff. Okay. All right, so here's the function, generate RSA key pair. This function will generate RSA key pair using this mechanism. This is the so these are the attributes that are set to the public key, and these are the attributes set to the private key. And once the key pair is generated, public key handle will be stored in H public, and private key handle will be stored in H private. Okay, let's keep moving. Okay, here's the function for encryption and the function to decrypt. Let's start with encrypt data. Inside encrypt data, there's a variable called mech of type CK mechanism. The value is CKM RSA PKCS. This is the variable, or sorry, this is the mechanism that the sample will use for encrypting and decrypting. This function starts with C encrypt init PKCS11 call that takes a session handle number, the mechanism, and the handle number of the public key. The next call is made for C encrypt. It takes the session handle number, the plain text, the size of that plain text. The fourth argument is going to be null because encrypted is currently not assigned enough memory. And ENClen is going to receive the length of encrypted data. And this length will be used to assign memory to encrypted. And then C encrypt is going to be repeated. So we will pass the session handle number, plain data, size of plain data, encrypted. This is a variable that will receive the encrypted data. And ENClen is going to be the length of that encrypted data. Once this data is encrypted, we will use print hex function to print the encrypted data as hex. Okay. Let's have a look and see what's happening inside decrypt data. So again, mech has a value of CKM RSA PKCS. We are calling decrypt init, passing the session handle number, the mechanism which I want to use for decrypting the data, and the handle number of the private key. The next call is for C decrypt. We are passing the session handle number, encrypted data, the length of that encrypted data, null because we currently the decrypted variable does not have enough memory, and DEClen is going to be the length of decrypted data. Once we receive the length of decrypted data, we will assign memory to decrypted and repeat C decrypt operation. C decrypt, session handle number, encrypted data, encrypted data length, decrypted data, and the decrypted data length. Once this data is decrypted, it's going to print that data as hex. And then inside the main function, load library, connect to slot, generate RSA key pair. Then it's going to display the plain data or a plain text as hex. Then it's going to encrypt data. It's going to decrypt that data, disconnect from slot, and the code ends. Let's compile this code. So to compile it, hold on. Slot number. Okay, so G++ CKM RSA PKCS.cpp, and I'm going to output this inside RSA PKCS. Include all header inside include directory d next. Okay, CKM RSA PKCS. Here's the slot number. Normal user. And here's the output. So this sample first generated the RSA key pair, and it displayed the plain text as hex. It used the public key to encrypt this plain text, and then it used the private key to decrypt that encrypted data. And as you can see, the plain text matches with the decrypted data. Okay, and the last sample that I have for today's video is also based on RSA. So I'll be using CKM RSA PKCS OAP.cpp. This is the sample. So this sample will generate RSA key pair, and then it will use that RSA key pair to perform some encryption using CKM RSA PKCS OAP mechanism. Now, most of the code in this sample is same as the previous code that I discussed. So I'll just show you what's different in this code. And what's different is, okay, so all of this is same. What I've added is OAP param. So this is a variable OAP param of type CK RSA PKCS OAP params. This is a structure in PKCS11, which is used for passing OAP parameters. Let me show you something. If you want to read more about this structure, this information is available on page 200. This is the structure. Now, OAP stands for Optimal Asymmetric Encryption Padding. I want to make a separate video about RSA OAP and RSA PSS. So I will not get into the details of this mechanisms right now. If you want to read about the structure, it's on page 200. Let's go back to the code. So this variable will contain all information about OAP parameters. Let's scroll down. Okay, connect to slot, disconnect from slot. And here's the function that will generate RSA key pair. It's the same function. Okay, so I have a separate function for initializing OAP parameter. Now, in order to perform encryption using RSA PKCS OAP mechanism, I need OAP parameter. And this function will initialize OAP parameters with all necessary values. And like I said before, I will talk about OAP and PSS padding in another video. Okay. So inside encrypt data, first this function will initialize OAP parameter. Then there's a variable called mech of type CK mechanism. And I'm passing CKM RSA PKCS OAP. I'm also passing OAP parameter and the size of OAP parameter, the structure. And then I'm calling C-encrypt init function, which has session handle, mechanism, and the handle number of the public key passed as arguments. After that, we have C-encrypt that takes 5 arguments. 8 session is the handle number. Plain data contains the plain text. This line is going to calculate the size of that plain text. I'm going to pass null here because encrypted does not currently have memory assigned. ENCLEN is going to receive the length of encrypted data, and we will use this information to assign memory to encrypt it. Let me scroll down a little bit. Okay, so once the memory has been assigned to encrypt it, I will repeat cencrypt call, session handle number, plain text, size of plain text, encrypted. This is the variable which has the memory assigned to it, and the length of that encrypted data. Once this plain text has been encrypted, it's going to print the encrypted data as hex. Okay, same thing is happening inside decrypt data. I'm declaring a variable called mech, which is of type CK mechanism. And I'm passing CKM RSA PKCS OAP as the mechanism that I want to use. OAP param is going to be the parameters used for OAP encryption and decryption. And I'm going to pass the size of OAP param. Then I'm calling C decrypt init. This has 3 arguments: session handle, mechanism, and the handle number of the private key. Immediately after that, C decrypt is going to be called. This will have 5 arguments: the session handle number, encrypted data, length of that encrypted data. I'm going to pass null because decrypted does not have memory assigned to it. And DECLEN is going to receive the length of the decrypted data. I'm going to use this information to assign memory to decrypt it. And after that, I will call C decrypt again. This time I'm going to pass all information I have. So the session handle number, encrypted data length, decrypted. This is the variable that will receive the decrypted data, and the length of that decrypted data. And once the data has been decrypted, it's going to print that information as hex. And then finally, in the main function, I'm loading the library, connect to slot, generating the RSA key pair, printing the ciphertext as hex, calling encrypt data, calling decrypt data, and finally disconnect from slot, and the code ends here. Okay, let's compile this code. So SoftHSM util show slots. Here's the slot number, clear the screen. Okay, so CKM RSA PKCS OAP, and I'm going to output this inside CKM RSA PKCS OAP. Include all headers from the include directory and D next. Okay. And paste the slot number. Normal user is a user password, and I'll hit enter. And here's the output. So here's the plain text. Here's the encrypted data, and here's the decrypted data. And as you can see, this decrypted string matches with the plain text. And that wraps up today's video. If you have any questions, please drop them in the comments below. I will do my best to answer them as soon as possible. I hope you found value in this video, so please like this video if you liked it, and subscribe to my channel if you're new here. I'll talk to you in the next one. Bye bye.